So I'm Bobby, and I'm going to talk to you today about compacting the uncompactable and providing memory compaction for C and C++ programs. And I want to start out today by starting with a story. And this story is The Impossible Dream. There's an older version of this story that stars Don Quixote, the man of La Mancha. And in this older version of the story, he wants to either reconquer or reintroduce chivalry to all of Spain. Today, though, the version we're going to talk about features the malloc of La Mancha. And rather than reconquer all of Spain, we want to allocate all of Spain. So in this story, here we have Spain. And when our hero gets malloc requests, he looks around on a map, and they find free chunks of Spain and hands them back to whoever requested it. And at the beginning of the story, this process is pretty easy. We can just sort of march on down the map here, allocating the next free chunk we find. However, over time, some of these old areas that we had allocated are no longer needed and are freed. And so eventually we end up in a situation where we have little chunks of free space spread throughout the map here. And we get a new request. We get a new large allocation request. And unfortunately, we don't have enough free space here that's contiguous, that's near each other, to serve this request. What our hero really wants to do is to somehow be able to move these existing requests together, which consequently will move all of our free space together so that we can serve this request. Unfortunately, this is not that simple. If you imagine in the real world, if you purchase some land to build a house, you build a house there, you start raising a family in this house, and then someone shows up and tells you that actually your land is 4 miles to the left, you're going to feel very angry and sad, and that's basically what a segfault feels like to a program. So we can't do this. And this problem that we're talking about is memory fragmentation. And what memory fragmentation is when a program requires much more memory from the operating system than the sum of the live objects that you're working on, when this ratio is much greater than 1. And there's actually strong theoretical bounds dating all the way back to 1977 with Robson that show that fragmentation in programs written in languages like C and C++ with non-moving allocators, that this fragmentation can be over an order of magnitude, can be up to 13x. And it's related to logarithmically to the size of the largest size class over the smallest size class. And when we talked about moving things together, what this is memory compaction. And what this would let us do is move our live objects together to give the rest of that memory back to the operating system so that the operating system could use it for other programs or better purposes. In the original version of this story, Don Quixote tilts at windmills, right? He fights imaginary enemies. But unfortunately, one of the other differences in our modern story is we have some real enemies or foes. This is Ken Thompson and Dennis Ritchie, who have invented the C programming language, which is sort of the root of our woes here. But it's not only the C programming language. There's languages built on top of this, C++, that feature manual memory management. And more recently, there are languages like Rust and Swift that automate some of this memory management, but don't have moving memory allocators that have chosen to under the hood, manually manage memory. And Chris Latner is the developer who created LLVM and then created the Swift programming language and talked about why a modern programming language created in the last few years would choose to forego using a garbage collector. It would choose to forego some technology that might help us here. And he has a bunch of great points, but one of the big ones is that in order for garbage collectors to run efficiently and serve your allocation requests efficiently, they require 3 to 4x more memory than other solutions. So you're required with a garbage collector to have a bunch of free space sitting around. And this is at odds with what a lot of people want, both on mobile devices as well as on the server and on desktops, which is minimizing memory usage. And Chris actually quoted my advisor and collaborator on this work, Emery, some work he had done that quantifies these performance impacts. And on top of these programming languages, we have lots and lots of software in use today that's written in them, right? Our databases are written in C and C++. Our web browsers, our spreadsheets, lots of applications that we interact with every day potentially suffer from these problems and don't have a solution to fragmentation. But it's not only applications written in C and C++. There are other programming languages like Ruby and Python here that actually the interpreters that people use for these languages every day are themselves C programs. And under the hood, if you ask for large objects, it will call malloc. So on the other side of the fence here, we have some languages that are able to address this problem, right? We're not the first people to wonder about fragmentation or hope to provide compaction. And these languages have solved this with garbage collection. Because they have a garbage collector, they're able to move objects closer together. And to understand why we can't just adapt existing solutions for our C and C++ programs, let's look at what compaction looks like under a garbage collected language. So we have three things going on here. We have operating system pages. We have live objects that are smaller than the operating system page. And we have references. We have pointers between objects. And what the garbage collector is going to do, what the runtime is going to do here, is it's going to want to move these objects closer together to free up one of these pages to give it back to the operating system. And every time our runtime moves an object, the key thing here is that it has to update every single reference, every single pointer that points to that object to make sure that there are no memory safety errors, right? And once it's done this, we're left with a free page that we can return back to the operating system. So back in C and C++ land, things are a little bit different. Rather than this sort of strong runtime that Java and .NET provide, instead, we compile C and C++ programs down to machine code. And often even, we strip any sort of symbol information or debug symbols from the binary before sending it out and running it in production. Right? This is just extra bytes that we don't want to ship across the wire sometimes. And so when we run these programs, the sort of real problem here is that we can't distinguish what's a pointer from what's application data. And so let's sort of look at what this means. Imagine we have an allocation that lives at address, this address starting with dead. And we want to move it to this other address at beef. Now, if we scan through an application's heap and we find 4 bytes that look like this pointer, we actually, from the memory allocator's perspective, we can't really tell if this is a pointer or if this is just application data, right? This may just be somebody's password, somebody's favorite phrase, or some numerical data that just happens to look like a pointer. We can't precisely say yes or no whether this is a pointer. And if we can't even identify what is a pointer, we can't safely update it. But lest you think like, OK, maybe we can just solve this with some additional work in the compiler by maybe passing more type information around, or alternatively, maybe if we just don't strip debug symbols, we can solve this in a pretty good way. It's unfortunately not to be. This is some code I pulled off of Stack Overflow. And one of the things about C and C++ developers is they really like being efficient. Right? C and C++ developers, myself included, love being efficient. And so this developer has realized that if you look at the spec for the language, it says that any requests that come back, any pointers you get back from malloc, are at least 8-byte aligned. And what this means is that the lowest 3 bits of any pointers you get from malloc are always going to be 0. Well, if they're always going to be 0, maybe we can just use those to store some flags. Imagine we have some Boolean flags. If we can store them in the pointer, we can use a C union type to sort of nicely manage this, and then just mask out those bits before we actually want to use the pointer. And this saves whole bytes, right? Whole bytes on every single object that we want to manage this way. And this code lives in the real world. There's lots of examples like this. So this means that if we're trying to look through the heap and find pointers, we can't even necessarily find all of the pointers, right? They may not look like pointers until they're actually immediately about to be used and sitting in a register somewhere. So this is sort of the environment that a memory allocator has to live in and has to work in if it wants to provide compaction. And that's why existing techniques don't really apply here. Which brings us to mesh. Mesh is our memory allocator for C and C++, our drop-in replacement for malloc that is able to provide compaction without having to do any relocation, without having to identify or move any pointers. Mesh works without having any without requiring any code changes. So we don't require you to remove those pesky union types. It doesn't even require recompilation. You just have to link against libmesh or even just LD preload libmesh and go. Your program will use our versions of malloc and free and the other related memory allocation functions to provide compaction. So we ran a web benchmark in Firefox. We ran speedometer. It's a well-known web benchmark. I think it runs a lot of sample to-do list applications in a row a bunch of times to test how fast the browser is with DOM manipulation and JavaScript and a mix of all of that. And we saw that over the course of this benchmark, when Firefox used libmesh, there was on average a 17% heap size reduction. The score reported by speedometer at the end of this was within 1% of Firefox with its default allocator. Redis is an in-memory key value data store. And one of the ways that people can use Redis is as an LRU cache. So you can tell Redis, hey, I want you to store objects in a cache-like manner, but use at most, X number of megabytes of memory. And if I go to insert more objects that would overflow this size, kick out some old objects. And so people reported to the Redis GitHub, opened up GitHub issues and said, hey, when we do this, we see actually a lot of memory fragmentation. Redis developers were able to pull this down into a reproducible test case, and they actually wrote their own application-specific defragmentation routine. That depends on the fact, essentially Redis with some, to a first approximation, is a very large hash map behind a socket. And they take advantage of the fact that this is sort of a very specific heap layout to code up a defragmentation routine that works with the default memory allocator and is able to recover from compaction in this case. On this graph here, the blue line at the top is what the memory usage of Redis over time looks like under this test case without defragmentation. There's a dotted red line in the middle here, which is what the heap usage over time looks like with Redis's defragmentation routine, and green at the bottom is mesh. So we're able to recover as much memory as this application-specific defragmentation routine in a completely generic way. But not only that, we're able to do it much, much faster. So we're able to do it with 5x less cycles spent performing compaction, which is great because Redis is single-threaded, so any time it's spent doing compaction is time that it's spent not serving requests. So in order to provide this compaction for C and C++, there were 3 challenges we had to solve. The first is we had to find a mechanism to compact the heap together, to compact pages in the heap together that didn't require updating pointers. Next is that we had to make sure that if we're experiencing fragmentation, that we could always apply this mechanism to recover from that fragmentation. And finally, the last key piece here is searching. We had to have some way to efficiently find pages in the heap that we could compact together that were eligible for this technique. And I'm doing a little bit of genre mixing here, but these 3 pieces combined together give us this ability to perform what we call meshing, which is compaction without virtual relocation. And so let's dig into the mechanism here first. We say that pages are meshable when 2 things hold. The first is that these pages have objects of the same size class. We don't consider meshing pages in the heap together if they hold objects of different sizes. And we'll talk about why that's not a problem in a few minutes. But the second constraint here is that all of the live objects across these 2 pages have to have non-overlapping offsets. There can't be any duplicate offsets if you count the object from the start of the page. And these 2 pages meet those requirements. So let's look at what happens when we have candidate pages here. The first thing to think about is that there's kind of two views of memory, right? There's virtual memory, which is the heap from the perspective of a program, and then there's physical memory, which is the fact that somewhere in your computer, in some RAM chips, these bits and bytes live, right? And when we talk about not being able to change pointers or move things, we're really talking about things from the virtual memory perspective, from the application's perspective. So the first thing we do to provide compaction is we mark one of these pages as read-only. And this prevents concurrent writes to objects while we're performing meshing. The next is that we copy objects from one physical page to the other while maintaining the object offsets from the start of the page. So if we have some objects on the left and we have some objects on the right, because none of these object offsets overlap, we can sort of mesh them together, right? And maintain their relative positions here. Next, we can update the processes. We update the processes page tables to point both of these virtual pages at the same physical page. And we're able to do this with a call to the mmap, with an mmap system call. And in particular, we're able to have this sort of fine-grained control over page tables because our heap is backed by an in-memory temporary file that's mapped into the process's address space with the map shared flag. And that gives us this mechanism to sort of directly poke at the page tables. Once this has happened, we can mark this source page that we copied objects off of. At the virtual layer, we can mark this read-write again, and any concurrent writers can now sort of proceed on their way. And we're left with a free page that we can give back to the operating system here. That is no longer a reference from the virtual address of our program. And the operating system now is free to use this for a different program, but it can even give us back this physical page in the future for use in a different size class. And again, just to highlight, because we've maintained these object offsets, no virtual addresses of these objects were changed, and so we didn't have to even identify pointers in the process's heap. So this is great. We now have a mechanism to do this compaction, but it's somewhat easy to imagine a worst case scenario. Imagine you have a number of pages. They're all very low occupancy. They all only have a single object on them, but that object is in the first object offset, right? They're all sort of conflicting, and they don't meet our requirements for meshing. And instead of two objects, you might have many of these. Instead of two pages, you might have many of these pages. And this isn't just sort of a fun to think about hypothetical problem. It's something that can actually occur with standard allocators. So if you call mesh a number of times in a row with the same size request, imagine you're asking for 256 byte objects, you will often get back a number of contiguous pointers in memory. And to avoid this worst case scenario, mesh uses randomization to ensure that we actually don't do this. We don't give out consecutive addresses in memory, but we spread allocations across the page uniformly. And we were able to write a very simple Ruby program. I think it's about 30 or 40 lines. It does a bunch of nice, clean, functional programming type operations, maps, and exhibits fragmentation in exactly this way. And we built mesh in sort of two configurations to test this out. We built it in the normal way, and then we also built it with randomization disabled. And when randomization was disabled, we weren't able to recover any memory. But with randomization enabled, we were able to recover about 20% or so of the heap size. So randomization really works and is necessary in this case. Which brings us to sort of, how do we do this? How do we sort of efficiently add randomization to our allocator? Previous approaches use something called random probing. In random probing, when you call malloc, you have this sort of pseudocode here where there's a while true loop. You generate a random offset, and you just check to see, is the slot sort of at this offset free? If so, give back a pointer for that position. Otherwise, try again. Go to the top of the while loop, and eventually you will find a free spot to return. Die hard, a memory allocator to sort of probabilistically let programs continue executing in the face of memory errors did exactly this. This is how Die Hard did randomized allocation. And this while loop in your memory allocator may sound sort of a little, it may sound suspicious, but actually in expectation, as long as occupancy is low on these pages, we expect to only go through this loop once, twice, maybe 3 times, as long as we keep page occupancy low. And this is what Die Hard did. Die Hard made sure that once a page was, crossed some threshold of fullness, we started allocating out of new pages. This is directly at odds with what we're trying to do today, right, with this allocator, which is minimize heap usage. So we needed a different approach. And what we developed was something called the shuffle vector. Shuffle vectors provide this fast randomized allocation along with full page utilization. So shuffle vectors work like this. We find a candidate page that we want to allocate out of, and we pull those offsets down into a thread local array. And once we have them in the thread local array, we call shuffle. And this performs the Fisher-Yates shuffle to randomize the order of items in this list quickly. When a request to malloc comes in, we're able to basically just pull the first item off this list, do some very simple math to turn it back to a pointer, and give it back to the program. This is almost as fast as an allocator can get. When a program frees this address in the future, we just do the inverse of that math to get an offset from the pointer, stick it on the front of this list, and call shuffle 1. This is a single iteration of the Fisher-Yates shuffle that just randomly swaps what we've added with an item in the list. And this ensures that if we end up in low occupancy situations, we can always apply, with high probability, we can always apply this meshing technique to recover from fragmentation. So we have 2 pieces of the puzzle, and the last one is how we find pages to mesh. Stated a little bit more formally, what we want to do is we want to find a meshing. We want to find a list of sets of pages to mesh that releases the maximum number of pages at a given point in time. And this is going to run in the free slow path. Every so often when you call free, we're going to do this. You could imagine this running in a separate thread, but that would require some amount of application-specific integration. And it's going to run at most once every 100 milliseconds. So I think the best way to sort of conceptualize this problem here is as a graph problem. This is sort of a visualization of this graph. In this graph, we have pages in the heap, and then we have edges between pages if there's a meshing relationship. And the great thing about graphs is that they're very well-studied objects, right? And we can think about applying existing techniques here. So one existing algorithm that would solve this problem exactly for us is called min-clique cover. A clique is a set of strongly connected nodes where they all have edges between them. And I've highlighted the min-clique cover solution here for all cliques of size greater than 1. So we could, each one of these independent sets of nodes, we could mesh together and free the maximum amount of pages back to the operating system. The small problem here is that min-clique cover is MP complete. It is computationally very hard in a rigorous sense. But actually, the fact that we're using randomization in our allocator comes back to help us. Randomization ensures that we can get away with solving a much simpler problem called matching. And the details of why we can solve this simpler problem are in an academic paper that we wrote on this that I'd be happy to talk to you about afterwards. So this is great. We can apply an existing algorithm, potentially, that is in NP. The problem is that, the last remaining problem here is that if we wanted to use an existing version of the matching algorithm, we would have to explicitly build this graph in memory. We would have to explicitly find all of these edges in memory before we could run the algorithm. And building this graph would require time, but more importantly, it would require space, right? We would have to allocate space to store this graph. And it turns out that if you wanted to allocate space to store this graph, it would vastly exceed the amount of memory that we would get back from from the result of this algorithm. So we needed something else, and we came up with an algorithm called split mesher. And split mesher is an approximation algorithm that approximates matching without having to actually build this graph in memory. And the function signature looks like this. It takes a set of partially full pages, and it returns pairs of pages to mesh. And the way it works is as following. We sort of take that input, we split it into two lists, two sort of arbitrary lists, and then we iterate, comparing A sub I to B sub I, and then comparing the item on the left to the item on the right. And we just check to see, is there an edge there? Are these pages meshable? And we can do this efficiently with, we have bitmaps that store information on occupancy for pages, and we can use CPU intrinsics to do this quite fast. When we get to the bottom of this list, we actually just return to the top, increment the offset on the right by 1, and continue marching down. And the key thing here is that we do this a fixed number of times. We do this incrementing of B sub I on the right a fixed number of times that is independent of the input, which means great things for runtime that we'll talk about in a second. But if we find a pair of pages that have a meshing relationship that we can compact together to free space, we remove it from the list, we stick it off to the side to return later, and then we just continue on. And we show that actually split mesher runs in linear time with respect to the input, with respect to the size of the heap, and the running time is also sort of dependent on the global probability of spans meshing. So it's also proportional to sort of how fragmented the heap is. But the really great thing here is that not only does this run quickly, but we have very strong bounds on how good of a match that we find. And we show that this is actually an arbitrarily close to 1/2 approximation with high probability, which has a lot of hedging words, but they're all very precise words. Essentially, it means that we make sure that we find a solution that is at least half as good as the optimal solution every time we run this algorithm. And that's why we're able to sort of do so well with a general technique compared to even application-specific techniques that encode a bunch of information about sort of the precise heap layout and types of things. And we do this efficiently. We do this with much less CPU time spent compared to, in this example, Redis's case. The graph on the left here shows insert time during this test case, during this LRU test case. One of the worries that we and reviewers had was that adding randomization to our allocator would somehow decrease locality and slow things down on average, either because finding random numbers in the allocation path is more expensive than not using randomization, but maybe there's some locality question here as well. But it turns out to not be the case. There's a very, very, very small impact on insert time in Redis caused by our allocator. And then, again, just to recap here, we're able to save significant space on applications like Firefox that have spent years trying to sort of decrease their heap usage over time, right? Firefox was, I think there was like a several-year project to reduce the heap size there. And finally, I think maybe I'm excited about all of this, but maybe most excitingly, we can provide compaction for dynamic languages like Ruby and JavaScript for free without having to touch or change the existing garbage collector here, just by using a different memory allocator under the hood, which is quite neat. And so you can find out more at libmesh.org. This links to our GitHub page. It's open source. You can download it and play with it. And it also links to our academic paper from there. So thank you very much. Yeah, we have some time, so I would be happy to take questions. I saw that hand first.
So you're framing physical pages, but it also seems like that you end up actually leaking virtual pages. Is there like a bounds to how far, how many virtual pages you can leak?
So the question is that the observation is that we're sort of compacting and freeing physical pages but not virtual pages. And are we leaking those virtual pages, and what's the impact of that? Did I state that?
Like Linux, for example, has 128 terabytes of mass.
Yep.
There are scenarios where you run into that.
Yeah, so I think the interesting limits here are that Linux, today we ran this mostly under Linux, but it also runs on Mac OS. Under Linux, there's a maximum amount of memory that the kernel will allow to store page tables. And if you have a very fragmented program and you don't adjust the defaults, this can be quite low and you can hit this. And we sort of detect that and make sure to not do bad things there. But what we also do is once imagine you've compacted several pages together, once you free all of the objects on those pages, we reset the mappings to the identity mappings between virtual and physical pages so that in the future, those work kind of as you would expect. I saw the black shirt back there.
Does mesh have any effect on issues like cache coherency?
Issues like, so the question is, does mesh have any effect on issues like cache coherency? I think the answer is no. But I also am not deeply, intimately familiar with cache coherency. So maybe we can talk after this. But I think the answer is no because of the marking pages as read-only before we perform this physical page movement. So we ensure sort of in a somewhat pessimistic way that we never see writes to these objects while we're moving them around physically until they're already moved, and then we mark them as read-write again. Thanks. Maybe one other thing there is I believe that it depends on whether caches are like physically or virtually tagged. And because we're moving things around physically and most, let's talk afterwards. But I think we're good. Yes?
So you mentioned that doing the meshing off-thread would require application coordination.
Yep.
About why that is?
Yeah, so the question is why would doing mesh off thread require application coordination? And the answer is that C and C++ programs make assumptions that when the main thread runs, it is the only thread running. And if your library starts up a thread before main runs, you can do initialization of libraries before main runs, things blow up. Firefox, for example, does some sandboxing of itself, and if there are and sandboxing on Linux works in weird and terrible ways in that it works sort of thread specifically. So Firefox is unable to successfully sandbox itself if there are other threads running, because what it wants to do is sandbox the main thread, and then after it's in that sandbox for that thread, spawn other threads which end up in the same sandbox. So it's things like that. Just sort of general assumptions that these programs make that mean we have to do sort of pessimistic things like not start up threads on our own.
Can you lazily spawn a background thread?
The question is, can we lazily spawn a background thread? I roughly feel like I tried this and it didn't work out well, but I don't remember the specifics. That was a long time ago, and I think in anger we just said, well, we'll just do it in the free slow path, and it happens rarely enough that it's not a large concern. Yes. Uh-huh.
Yeah, so my question is about the virtual page when you set it read-only.
Yep.
Could there not be another thread in the application that tries to access it during that time? What happens if it tries to write to it while it's read-only?
So the question is, what happens if another thread tries to write to this page that we've just marked read-only? And the answer there is that we install a segfault handler. It triggers a segmentation fault, or it triggers a signal. The operating system / CPU pause it at that instruction. Our handler runs, and then our handler, through very careful coding, waits until this meshing operation is done before returning from the handler. And there's a way to return from a segfault handler that says, actually, things are fine. Just try that exact instruction again. And when it tries that instruction again, after this has been completed and after that page is read-write, everything works as normal.
What if the application already has a segfault?
So the question is, what if the application is a segfault handler? And the answer is that we will nest segfault handlers. So we will we try to check very specifically to say, is this segfault actually because this page is read-only due to an ongoing meshing operation? And if not, then we either crash the application or call the application segfault handler. Yep. Yes.
What would you like operating systems to do to make building this kind of system simpler?
So the question is, what could operating systems do to make this building this simpler? I think one of the biggest things is some bulk way to update page tables. What we do right now is every single pair of pages to mesh, we have to do this dance of updating that, and that's significant cost because every time we update these page tables, we have to, the operating system under the hood does like a TLB flush, which is a synchronous operation across all processors. So if we had some bulk way to say, we have the results of this split mesher algorithm, we know we want to mesh all of these. If we could mark everything as read-only at once, update all the page tables at once, and then unmark things at once, I think that would significantly speed things up. Yeah. Yes?
Why isn't Firefox using it?
Why isn't Firefox using it? That's a good question. I believe we had some email discussions with them. It's a relatively new allocator, and I'm not sure in particular. I don't work for Mozilla, and in general, just speaking in general, it's nice to continue to use things that you deeply and intimately are familiar with. I would love to talk more with people from Mozilla about what we could do to sort of prove this out and see if we could run Firefox with it. Yes. Yes.
You mentioned that this was like a generic approach.
Yep.
If the application is already doing stuff with virtual memory allocation, what does your allocator do?
So the question is, what if the application is doing some of its own stuff with virtual memory allocation? Do you have an example?
Game engines sometimes reserve a whole bunch of stuff.
Uh-huh.
And then do weird things like do a giant ring buffer with multiple pages so that when it you don't have to deal with the concern that you might run out of memory.
Got it.
You keep allocating over and over again as long as you don't care about the beginning part, stuff like that.
Right. So to summarize, sometimes game engines in particular do things like create circular ring buffers so that an overflow on one side just sees the beginning of the array or something like that. All of that is fine. My rough understanding is that applications that do things like that will allocate their own memory with mmap. In general, you don't allocate something through malloc and then futz with the...
You're hijacking malloc and not anything.
Yeah. We replace malloc and the malloc-related calls, and any direct calls to mmap, an application is free to continue doing. Okay, right back there.
So with garbage collectors that you packing, it seems like it would replace a lot of that work. Is that just that overhead that they're incurring that isn't level?
So I think the question is can allocators that already do compaction use this technique as an alternative approach to?
I think the question is if this approach or garbage collectors that are implementing some form of compacting just doing extra work that would be better used just to run compacting.
Got it. So are moving garbage collectors just doing extra work if we can already do compaction this way? And I think the answer is no, because garbage collectors by necessity have to walk the graph of the heap to find out if objects are live. And so essentially, because they already have to sort of walk over either the entire heap or if it's a generational collector, the young gen, because they already have to do this, they can sort of relatively cheaply add in the moving and updating parts to that. That's my rough understanding. Okay, it's time. Thank you all again.